In Chapter 4, we have learned that there are only four basic forces in our universe: the gravitational force, the electromagnetic force, the weak nuclear force, and the strong nuclear force. Gravitational force is the weakest of the four basic forces. However, on the very large scale, as in astronomical system, the gravitational force is the dominant force determining the motions of moon, planets, stars, and galaxies. Our weight is the gravitational force due to the entire Earth acting on us. Gravitational force is always attractive. It acts at a distance without physical contact, and it depends only on the masses involved and the distance between them. To simplify the situation, we assume that the body acts as if its entire mass is concentrated at one specific point called the center of mass, that's Cm. Isaac Newton was the first scientist to precisely define the gravitational force, to propose an exact mathematical form, and to show that it could explain both falling bodies and astronomical motions. For two bodies having masses little m and capital M, with the distance r between them, the gravitational force is along a line joining the center of mass of these two bodies, and its magnitude is given by the equation for Newton's universal law of gravitation, where G is the gravitational constant and has been measured experimentally to be 6.674 times 10 to the minus 11 Newton meter square per kilogram square. A common misconception here is that bigger mass has larger gravitational force than smaller mass. In fact, if it is the gravitational force between the bigger mass and the small mass, the gravitational force on each object is the same, and this is also consistent with Newton's third law. It is interesting to know that the weight of an object mg is actually the gravitational force between it and Earth. We can substitute mg for F in Newton's universal law of gravitation, and it gives us this equation, where m, the little m, is the mass of the object, for example, this building. The capital M is the mass of Earth, and r is the distance between the centers of mass of the object and the Earth, which is exactly the distance to the center of the Earth. The mass of the object cancels, and we have G equals to gm over r squared. Plug in Earth mass and radius, we get the acceleration due to gravity g equals to 9.80 meters per second squared. And this value is independent of the object's mass. This shows that Newton's law of gravitation not only confirms Galileo's observation that all masses fall with the same acceleration g, but also explains the force that causes objects to fall in terms of this universal existing force of attraction between masses. Rearranging this equation, we can get m equals to gr squared over g, and this is a very useful equation and can be used to determine the mass of Earth, m. If we can measure the acceleration due to gravity g, the radius of Earth r, and the gravitational constant g correctly. Ocean tides are one very observable result of the Moon's gravity acting on Earth. Because water easily flows on Earth's surface, a high tide is created on the side of the Earth nearest to the Moon, where the Moon's gravitational pull is strongest. There is also a high tide on the opposite side of Earth because at that moment, the Earth is pulled toward the Moon more than the water on the far side. According to the simplified model, there are 2 high tides and 2 low tides per day at any location. The Sun also affects tides, although it only has about half the effect of the Moon. The largest tides, called spring tides, occur when Earth, the Moon, and the Sun are aligned. The smallest tide, called leap tide, occurs when the Sun is at 90-degree angle to the Earth-Moon alignment. Tides are not unique to Earth, but occur in many astronomical systems. The most extreme tides occurs when gravitational force is the strongest and varies most rapidly, such as near black holes. The tidal forces near them are so great that they can actually tear matter from a companion star. Talking about the gravitational force, there is one case about the apparent gravitational field experienced by astronauts orbiting Earth called weightlessness. Weightlessness doesn't mean that an astronaut is not being acted upon by the gravitational force. This term just means that the astronaut is in free fall, accelerating with the acceleration due to gravity. If an elevator cable breaks, the passengers inside will be in free fall and will experience weightlessness. You can experience short periods of weightlessness in some rides in amusement parks. A related term is microgravity, which refers to an environment in which the apparent net acceleration of a body is small compared with that produced by Earth at its surface. Many interesting biology and physics topics have been studied over the past 3 decades in the presence of microgravity. You may read the textbook for more information on this part. All the astronomical motions are governed by gravitational force. Although precise descriptions of complex systems must be made with large computers, we can describe an important class of orbits here without the use of computers. If the system has a small mass, orbits a much larger mass. This allows us to view the motion as if the larger mass m were stationary, and an inertial frame of reference can be placed on this larger mass. Also, the system has to be isolated from other masses. This allows us to neglect any small effects due to outside masses. There is a classical set of 3 laws called Kepler laws of planetary motion that describes the orbits of all bodies satisfying these 2 conditions. Kepler's first law states the orbit of each planet about the Sun is an ellipse with the Sun at one focus. Please note here that the Sun can be replaced by the larger mass m in any system satisfying these two conditions. For example, in the Earth-Moon system, according to this law, it means the orbit of the Moon about Earth is an ellipse with Earth at one focus. Kepler's second law states, each planet moves so that an imaginary line draws from the Sun to the planet sweeps out equal areas in equal times. As shown in this figure, if the shaded regions have equal areas, it takes equal times for the planet M to go from A to B, or from C to D, or from E to F, so that the planet M moves fastest when it is closest to the large mass M. Kepler's third law states, the ratio of the squares of the periods of any two planets about the Sun is equal to the ratio of the cubes of the average distances from the Sun. This is the equation form, where T is the period, that is, time for one orbit, and R is the average radius. This equation is valid only for comparing two small masses orbiting the same large mass. Actually, if we simplify the orbit of the planet to be circular orbits, we can do a little calculation and get a relationship like this. This means that if R and T are known for a planet or satellite, then the larger mass M can be calculated. You may read the textbook for more information about this part.